Right now, invisible cosmic forces could be aimed directly at Earth. In the time it takes you to listen to this sentence, gamma rays from distant black holes have traveled billions of light years through space, carrying energy that could sterilize our planet in seconds. These aren't theoretical dangers from science fiction. They're measurable phenomena that astronomers detect weekly, sometimes daily. The universe operates on scales that dwarf human comprehension. A single gamma ray burst releases more energy in 10 seconds than our sun will produce in its entire 10 billion year lifetime. These cosmic lighthouses sweep across the galaxy, and we're only beginning to understand their true nature. In December 2004, a magnetar just 20,000 light-years away sent a pulse of gamma rays toward Earth. The burst lasted 0.2 of a second, but it was so intense it temporarily blinded several satellites and caused measurable changes in our planet's upper atmosphere. If that same magnetar had been located just 1,000 light-years closer, the radiation would have stripped away our ozone layer entirely. This event wasn't predicted by existing models of stellar evolution. It challenged our understanding of how matter behaves under extreme conditions. Most concerning, it demonstrated that cosmic catastrophes don't announce themselves with warning signs we can interpret years in advance. Gamma-ray bursts fall into two distinct categories, each presenting unique threats to planetary life. Short bursts, lasting less than 2 seconds, appear to result from the collision of neutron stars or the merger of a neutron star with a black hole. Long bursts, extending from 2 seconds to several minutes, seem to accompany the collapse of massive stars into black holes. The physics underlying these events pushes matter to its absolute limits. When a star 30 times more massive than our Sun exhausts its nuclear fuel, gravity wins the ultimate battle. The stellar core collapses in less than a second, compressing material denser than atomic nuclei into a region smaller than Manhattan. This collapse doesn't happen uniformly. The star's rotation focuses the released energy into twin jets that punch through the stellar envelope at nearly the speed of light. These jets carry magnetic fields billions of times stronger than Earth's, accelerating particles to energies that shouldn't be possible according to classical physics. The resulting gamma-ray burst creates a beacon visible across the observable universe. If you could observe the gamma-ray sky with your naked eye, these bursts would appear brighter than the full moon, despite occurring in galaxies billions of light-years away. The energy density in these jets exceeds anything we can replicate in particle accelerators. Most gamma-ray bursts occur in distant galaxies, their effects diluted by cosmic expansion. But our own Milky Way contains thousands of stars massive enough to produce these events. Current estimates suggest that a nearby gamma-ray burst capable of affecting Earth's biosphere occurs roughly every few hundred million years. The geological record provides unsettling evidence that such events may have already shaped life on our planet. The Ordovician mass extinction, which eliminated nearly 85% of marine species 450 million years ago, coincides with chemical signatures that suggest massive ozone depletion. No terrestrial cause adequately explains the scale and timing of this environmental catastrophe. A gamma ray burst directed at Earth would not announce itself with visible light. The high-energy radiation would arrive first, traveling at the speed of light through interstellar space. Our atmosphere would absorb most of this energy, protecting us from immediate radiation poisoning but triggering a cascade of chemical reactions that would destroy the ozone layer within hours. Without ozone protection, ultraviolet radiation from our own sun would become lethal. Land-based ecosystems would collapse within months. Ocean productivity would plummet as ultraviolet light penetrated deeper into marine environments, disrupting the microscopic organisms that form the base of the food web. The aftermath would persist for years. Nitrogen oxides created by the gamma-ray interaction would form a brown haze in the stratosphere, reducing global temperatures and further stressing surviving ecosystems. Even if some life survived the initial radiation exposure, the altered climate would create conditions unlike anything in Earth's recent history. Detecting gamma-ray bursts requires specialized instruments that can distinguish these events from other high-energy phenomena. The SWIFT satellite, launched in 2004, can pinpoint the location of a gamma-ray burst within minutes and alert ground-based telescopes to observe the fading afterglow. This rapid response capability has revolutionized our understanding of these cosmic explosions. Observations reveal that gamma-ray bursts don't occur randomly throughout the universe. They cluster in regions of active star formation, where massive stars live fast and die young. Our solar system's location in the Milky Way's spiral arm places us in precisely such a region, surrounded by star-forming nebulae that continuously produce the stellar giants destined for catastrophic collapse. The energy released in these events defies easy comprehension. A typical long gamma-ray burst converts roughly 1% of the progenitor star's mass directly into energy, following Einstein's famous equation E equals mc squared. This means that a star 20 times more massive than our Sun releases energy equivalent to the complete annihilation of 2 Earth masses. This energy doesn't radiate uniformly in all directions. The jets that produce gamma-ray bursts are remarkably narrow, typically spanning only a few degrees of arc. This focusing effect means that the energy density within the jet can exceed the total energy output of our Sun by factors of millions or billions. The magnetic fields that shape these jets reach strengths that challenge our understanding of how matter behaves. Laboratory experiments cannot replicate such extreme conditions, forcing theorists to rely on mathematical models that may not capture the full complexity of the physical processes involved. We're essentially trying to understand the universe's most violent events using equations derived from much gentler phenomena. Recent observations have identified a new class of gamma-ray bursts that don't fit established categories. These events, dubbed ultra-long bursts, can persist for hours rather than seconds or minutes. Their energy output and duration suggest they arise from mechanisms we haven't yet identified, possibly involving the birth of black holes with unusual properties. The discovery of these ultra-long bursts highlights how much we still don't understand about cosmic explosions. Each new observation reveals unexpected complexity in phenomena we thought we had characterized. The universe consistently surprises us with its capacity for violence and its indifference to the life it occasionally nurtures. Perhaps most unsettling, gamma-ray bursts represent just one category of cosmic threat. They are the events we've learned to detect and partially understand. The universe may harbor other forms of instantaneous, long-range destruction that we haven't yet recognized or imagined. As we peer deeper into space with increasingly sophisticated instruments, we're not just mapping the cosmos. We're taking inventory of the weapons that surround us, cataloging the forces that could end our civilization without warning. The question isn't whether such threats exist, but whether we can identify and prepare for them before they find us. 26,000 light-years from Earth, at the gravitational center of our galaxy, lies Sagittarius A star. This supermassive black hole, containing the mass of 4 million suns compressed into a region smaller than Mercury's orbit, appears deceptively quiet. Current observations show it consuming matter at a rate that produces relatively modest energy output. But this apparent calm masks a history of violence that could resume without warning. Radio telescopes detect vast structures extending from the galactic center, fossil evidence of past activity that dwarfs anything we observe today. The Fermi bubbles, two enormous cavities in the hot gas surrounding our galaxy, stretch 25,000 light-years above and below the galactic plane. These structures contain energy equivalent to millions of supernovae, yet they appear to have formed within the last few million years. The physics of supermassive black holes creates conditions where small changes in matter infall can produce dramatic variations in energy output. When material approaches the event horizon, gravitational forces compress and heat it to temperatures exceeding 100 million degrees. This process converts matter to energy with an efficiency that makes nuclear fusion look wasteful. A black hole actively consuming matter becomes one of the universe's most powerful engines. The rotating accretion disk acts like a cosmic dynamo, generating magnetic fields strong enough to accelerate particles to nearly the speed of light. These relativistic jets can extend thousands of light-years, carrying energy across galactic distances. Sagittarius A star's current diet consists mainly of stellar wind from nearby massive stars and occasional small asteroids or comets. This sparse feeding produces X-ray flares that last hours or days, events we can observe with space-based telescopes. But the galactic center environment contains much larger potential meals. Within the central light year of our galaxy, astronomers have identified several molecular clouds containing thousands of Earth masses of gas and dust. These clouds follow elongated orbits that periodically bring them close to the black hole. When one of these clouds makes a close approach, the resulting accretion event could increase Sagittarius A star's luminosity by factors of millions. The aftermath of such reactivation wouldn't remain confined to the galactic center. High-energy radiation would propagate outward at the speed of light, while energetic particles would follow the galaxy's magnetic field lines. Our solar system's location in the galactic disk would place us directly in the path of this expanding wave of destruction. Evidence from other galaxies suggests that supermassive black holes undergo cycles of activity and dormancy. Active galactic nuclei, powered by supermassive black holes consuming large amounts of matter, can outshine their entire host galaxies. The energy output from these objects exceeds the combined luminosity of hundreds of billions of stars. Our galaxy's structure shows signs of past active periods. The central bar, an elongated concentration of stars that extends several thousand light-years from the galactic nucleus, may have formed during episodes of increased black hole activity. This bar structure continues to channel gas toward the center, potentially setting up conditions for future reactivation. The timescales involved in galactic center dynamics span millions of years, but the triggering events can happen suddenly. A massive star wandering too close to Sagittarius A star would be torn apart by tidal forces, feeding the black hole enough material to power intense activity for thousands of years. Such stellar disruption events occur roughly once every 100,000 years in a typical galaxy. Alternatively, the infall of one of the nearby molecular clouds could trigger reactivation on even shorter timescales. As the cloud approaches the black hole, gravitational forces would compress and heat the gas, creating conditions similar to those observed in distant quasars. The resulting accretion disk would launch jets of relativistic particles along the galaxy's rotation axis. These jets, if aimed toward Earth, would deliver a lethal dose of high-energy radiation. Unlike gamma-ray bursts from distant galaxies, radiation from our own galactic center would arrive with little warning and continue for extended periods. The proximity of Sagittarius A star means that even a modest increase in activity could have catastrophic consequences for life on Earth. Observations of active galactic nuclei reveal that these objects can vary dramatically in brightness over timescales of months or years. Some show increases of more than a factor of 100, while others dim by similar amounts. This variability suggests that the accretion process is inherently unstable, prone to sudden changes that we can't predict. The interaction between supermassive black holes and their surrounding environment creates feedback loops that can either suppress or enhance activity. When a black hole becomes active, the energy output can heat surrounding gas to temperatures that prevent further infall. Conversely, cooling gas can collapse toward the center, providing fuel for renewed activity. Current monitoring of Sagittarius A star focuses on detecting changes in its X-ray output and radio emission. These observations reveal a black hole that occasionally flares but generally maintains relatively low activity levels. However, our monitoring baseline spans only a few decades, a negligible fraction of the timescales relevant to black hole evolution. The Event Horizon Telescope has provided unprecedented views of the immediate environment around Sagittarius A star. These observations show a dynamic accretion flow with material spiraling inward on timescales of minutes to hours. The complexity of this environment makes it difficult to predict when or how a transition to higher activity might occur. Beyond our galactic center, the universe contains millions of supermassive black holes, many of which are currently active. Studying these distant objects provides insights into the range of behaviors possible for such systems. The most luminous quasars, powered by black holes consuming material at rates approaching theoretical limits, demonstrate the destructive potential of these cosmic engines. The transition from dormancy to activity in supermassive black holes appears to be a common phenomenon in the universe. Galaxy surveys reveal that many systems show evidence of past activity, while others are currently in active phases. This suggests that black hole reactivation is not a rare occurrence but a normal part of galactic evolution. One particularly concerning scenario involves the interaction between Sagittarius A star and nearby stellar mass black holes. The galactic center contains a dense concentration of these smaller black holes, remnants of massive stars that have completed their evolution. If one of these objects were to spiral into Sagittarius A star, the merger would release enormous amounts of energy. Such black hole mergers produce gravitational waves, ripples in space-time that we can now detect with instruments like LIGO. While these waves themselves pose no threat to Earth, the electromagnetic radiation accompanying the merger could be devastating. The energy release would likely trigger intense activity in any surrounding accretion disk. The challenge of predicting black hole behavior stems from the extreme physics involved. Near the event horizon, space and time become severely distorted, and matter exists in states that we can barely comprehend. General relativity provides the theoretical framework for understanding these phenomena, but the mathematical complexity often prevents detailed predictions. Numerical simulations of black hole accretion require some of the world's most powerful supercomputers. Even then, the calculations must make simplifying assumptions that may not capture the full complexity of the physical processes. We're essentially trying to predict the behavior of the universe's most extreme objects using approximations and incomplete theories. The discovery of intermediate mass black holes, with masses between stellar and supermassive scales, has added new complexity to our understanding. These objects, if they exist in significant numbers, could provide additional sources of high-energy radiation. Their smaller size would make them harder to detect but potentially more unpredictable in their behavior. As our observational capabilities improve, we're likely to discover that the universe harbors more varieties of black holes than we currently recognize. Each new class of object represents potential threats that we haven't yet learned to identify or understand. The cosmos continues to surprise us with its capacity for violence and its indifference to the life it occasionally nurtures. The question isn't whether supermassive black holes will become active again, but when and how such reactivation might occur. Our survival may depend on developing the ability to predict and prepare for these cosmic catastrophes before they overwhelm our defenses. Dark matter makes up 85% of all matter in the universe, yet it interacts with ordinary matter only through gravity. This invisible substance shapes the large-scale structure of the cosmos, but it may also harbor objects that could approach our solar system undetected. Among the most concerning possibilities are primordial black holes, formed in the early universe and potentially invisible to current detection methods. Unlike stellar mass black holes, which form from the collapse of massive stars, primordial black holes could have formed from extremely dense regions in the early universe. These objects might have masses ranging from microscopic scales to thousands of times the mass of our Sun. The smaller ones would evaporate quickly through Hawking radiation, but larger primordial black holes could persist for billions of years. Detecting these objects presents extraordinary challenges. A primordial black hole with the mass of a small asteroid would be smaller than a proton, making direct observation practically impossible. Even larger ones, with masses comparable to planets, would be detectable only through their gravitational effects on nearby matter. The gravitational influence of a black hole approaching our solar system would begin to affect planetary orbits long before the object became visible. Computer simulations suggest that a black hole with Earth's mass, passing through the outer solar system, could destabilize the orbits of the gas giants within a few million years. The resulting orbital chaos could eject planets from the solar system or send them careening toward the inner planets. More immediately threatening would be a close encounter with a stellar mass black hole. These objects, typically containing 3 to 20 times the mass of our Sun, exist throughout the galaxy in numbers that we're only beginning to estimate. Current surveys have identified several dozen stellar mass black holes, but theoretical models suggest that millions more remain undetected. The challenge of black hole detection lies in their fundamental nature. Without nearby matter to accrete, these objects emit no electromagnetic radiation. They become visible only when they interact with other matter, such as a companion star or interstellar gas clouds. Recent advances in gravitational wave astronomy have revealed that black hole mergers occur more frequently than previously estimated. The LIGO and Virgo collaborations detect several such events each year, suggesting that stellar mass black holes are common throughout the universe. Each detection represents objects that were previously invisible, highlighting how much we don't know about the population of black holes in our galaxy. The distribution of these objects within the Milky Way remains poorly constrained. They likely concentrate toward the galactic center, where stellar densities are highest, but significant numbers probably exist throughout the galactic disk. Our solar system's motion through the galaxy brings us into contact with different regions over time, potentially exposing us to varying levels of risk. A stellar mass black hole passing within a few light years of our solar system would begin to perturb the orbits of comets in the Oort cloud. This vast reservoir of icy bodies, extending halfway to the nearest star, contains trillions of potential projectiles. Gravitational disturbances could send swarms of comets toward the inner solar system, creating impact hazards that would persist for millions of years. The long-term stability of our solar system depends on the delicate gravitational balance between the planets and the Sun. Computer models reveal that this stability exists within narrow limits. A black hole passing through the outer solar system could alter planetary orbits in ways that accumulate over millions of years, eventually leading to planetary collisions or ejections. Even without directly entering our solar system, a nearby black hole could pose threats through its interaction with interstellar matter. The local bubble, a cavity in the interstellar medium that surrounds our solar system, contains hot, low-density gas that could be dramatically affected by a passing black hole. Changes in this local environment could alter the flux of cosmic rays reaching Earth. Cosmic rays, high-energy particles that constantly bombard our planet, are normally modulated by the solar wind and Earth's magnetic field. A significant increase in cosmic ray flux could affect atmospheric chemistry, potentially depleting the ozone layer and increasing radiation exposure at Earth's surface. The biological consequences of such changes remain uncertain but could be severe. The search for dark matter has revealed that our understanding of the universe's composition remains incomplete. Recent observations suggest that dark matter may interact with itself in ways that we don't fully understand. If dark matter can form bound structures, it might harbor objects that we haven't yet learned to detect. Astronomers have identified several anomalous gravitational effects that might indicate the presence of dark matter substructure. These observations challenge our models of how dark matter behaves on small scales. If dark matter can form dense concentrations, these objects could affect the motion of nearby stars and gas clouds in ways that we're only beginning to recognize. The possibility of primordial black holes as dark matter candidates has gained renewed attention following the detection of gravitational waves from black hole mergers. If a significant fraction of dark matter consists of black holes, our galaxy could contain billions of these objects. The statistical probability of a close encounter with Earth would be much higher than current estimates suggest. Surveys designed to detect dark matter particles have so far failed to identify the nature of this mysterious substance. Underground detectors, space-based instruments, and particle accelerators have all searched for evidence of dark matter interactions without success. This failure suggests that dark matter may be more exotic than we initially assumed. The implications extend beyond simple detection problems. If dark matter consists of objects rather than particles, our entire approach to understanding cosmic structure may need revision. The universe could contain populations of massive objects that we haven't yet learned to identify. Humanity's efforts to detect and track potentially hazardous objects focus primarily on asteroids and comets. These programs have identified thousands of near-Earth objects and continue to discover new ones weekly. However, black holes would be invisible to these surveys unless they were actively accreting matter. Developing detection methods for dark objects requires new approaches. Gravitational microlensing, where a massive object briefly magnifies the light from a background star, offers one possibility. Current microlensing surveys have detected several candidate events that might indicate free-floating black holes, but the interpretation of these observations remains uncertain. The Gaia spacecraft, mapping the positions and motions of over 1 billion stars, provides another tool for detecting dark objects. Subtle changes in stellar motion could reveal the gravitational influence of unseen companions. Analysis of Gaia data has already identified several candidate black holes, though confirmation requires additional observations. Future space-based gravitational wave detectors, such as the proposed LISA mission, would be sensitive to the signatures of black holes throughout the galaxy. These instruments could detect the gravitational waves produced when black holes interact with other massive objects. Such capabilities would provide early warning of potentially threatening close encounters. The development of defensive strategies against cosmic threats faces fundamental physical limitations. Unlike asteroids, which can potentially be deflected, black holes are essentially immovable. Our only defense against such objects would be advance warning and possibly evacuation. The timescales involved in cosmic encounters offer both challenges and opportunities. While a black hole might take millions of years to significantly affect our solar system, the early stages of its approach could be detectable decades or centuries in advance. This lead time could allow for technological development and preparation. However, the scale of the threat might exceed our technological capabilities. Moving human civilization to another star system would require advances in propulsion technology that remain far beyond our current abilities. Even preserving human knowledge and culture for future reconstruction would present enormous challenges. The study of cosmic threats reveals a universe that is both magnificent and terrifying. The same physical processes that create stars and planets also produce gamma-ray bursts and black holes. The cosmos operates according to laws that make no distinction between creation and destruction. Yet human civilization has already demonstrated remarkable resilience in the face of terrestrial catastrophes. Ice ages, volcanic eruptions, and asteroid impacts have all challenged our species' survival, but we've adapted and thrived. The same ingenuity that has allowed us to explore space and decode the universe's secrets may enable us to survive cosmic threats. Our growing understanding of these dangers paradoxically offers hope. Each new discovery improves our ability to predict and prepare for future threats. The same technologies that reveal cosmic hazards also provide tools for detection and, potentially, mitigation. The universe has existed for nearly 14 billion years, and it will continue for trillions more. In that cosmic perspective, human civilization occupies a brief moment. But within that moment, we have the opportunity to understand our place in the cosmos and to prepare for whatever challenges it may bring. The threats we face are real and immediate. Gamma-ray bursts, black hole reactivation, and dark matter encounters represent genuine dangers to our continued existence. But they also represent opportunities to transcend our terrestrial limitations and become a truly cosmic civilization. Our fate may ultimately depend on our ability to detect and understand these cosmic dangers before they overwhelm our defenses. The universe offers no guarantees, but it does provide the physical laws and resources necessary for survival. Whether we choose to use them wisely remains the greatest challenge of our time.